just to go forward and not spell forward. And this is the laser that's forward and back. Okay. Maurizio Pajola on the grooves on Phobos.
Yeah, so good afternoon, everyone. I'm really pleased to be here. I thank Yvonne for giving me the opportunity to talk. And what I'm going to show you today, after a presentation that I made last year on Phobos, it's the results I was getting with a group of people here on Phobos grooves, whether they are not the inherited signature of an ancient parent body. I thank all co-authors here, specifically Emanuele Simioni, Matteo Massironi, Gabriele Cremonese, and Monica Lazzarin, that helped me in doing this kind of work. It's not going. Yep. Yeah. No. And the presentation is done. Great, thanks. If you want to make any question. So, first of all, Phobos is in a nutshell. What's Phobos? Phobos is one of the two satellites of Mars. It has pretty big dimension. It is 26 kilometers per 18.4. It has a bulk density, which is one of the main important results on Phobos. It's a bulk density of 1.8 gram over cubic centimeter, and it's orbiting around 6,000 kilometers far from the Mars surface. It is well inside the Roche limit between Phobos and Mars, and it's orbiting more or less at the equator. Okay. Phobos, it's a really harsh field of work. I mean, it has a debated origin that it was presented before. It can be the result of a formation from a disk of debris, whether as a remnant of the formation of Mars, as presented by Safronov in 1986, or as the result of a collision between Mars and a large body. But the problem is that this is one point of view. I mean, the other one is that after 43 years of observation, there are physical characteristics and spectra similar to low albedo asteroids, such as C-type or D-type, pointing towards an asteroidal capture. The problem is that on Phobos, there is a main feature, which are the Phobos grooves. And as you can see, they are everywhere here on the surface, mostly everywhere, and I will show you a map later. This is a representation of the Viking map of a Mercator projection of all the grooves that are all around Phobos. And we are trying to understand if this is a common feature present and also on other asteroids or not. Yeah, grooves are a common feature on asteroids. Here you can see, for example, works on Gaspra, Ida, Eros, Lutetia, and Vesta. And you see that, for example, in the case of Eros, there are a huge quantity of folds and grooves going all around the object. Then on Vesta, too, there are equatorial folds here. And on Lutetia, with a work made by Bessa et al. And Massironi et al., there are also grooves. So it's not an uncommon feature present on asteroids. The problem is that Phobos is orbiting a planet, which is Mars, and it's not a single asteroid. I mean, so Phobos grooves were first observed in Viking images in 1977, and their origin is greatly debated. It's orbiting around Mars, and there is also a big crater on the surface of Phobos, which is the 9 kilometers big crater called Stickney. The origins of the Phobos grooves are several. First of all, it was proposed that their presence is due to the Mars tidal stress proposed by Dobrowolskis in 1982. Then there was the dynamic loading due to the impact originating the 9 kilometer Stickney crater, which is another possibility. Then Phobos grooves can be the results of secondary impacts related to the Stickney crater, or another work, secondary impacts resulting from primary impact events on Mars. It's Phobos like being a tennis racket just going there. There are impacts on the surface of Mars. And then Phobos orbiting around Mars takes all these boulders and pieces of rock from the surface going through it. Okay. So in a work presented in a great work presented in 2014 in Murray and Heggie, there is a summary of maps showing Phobos grooves. So I don't want you to go through the text here, just have a look at this map of Phobos grooves here. So the proposed Stickney ejecta after Thomas 1998 should be presented in this way. So you can see that they are typically completely different with respect to the map that were selected and the map that was created on Phobos grooves. Then the tidal stress on Dobrowolskis 1982 presents still some problems with respect to the results that we see on the surface of Phobos. About the rolling boulders or the Stickney fracturing related to the impact of Stickney, they seems not to be related to the Phobos grooves, or at least not the entire quantity of grooves that we see. Finally, there is these results of Marr in 1994 showing that the grooves of Phobos can be the results of secondary impact from Mars. The problem is that great work done by Ramsey et al. In 2014, it seems that the volume of ejecta coming from Mars to Phobos is insufficient to produce grooves as secondary impacts. So despite the fact that Stickney impact fracturing seems to be inconsistent with the grooves distribution on Phobos, we cannot rule out the possibility that grooves are representative of fractures and joint planes still holds. So what we are showing here in this work is that grooves can be the expression of fracture planes, and we derived a spatial distribution and orientation on 3D reconstructions. Just now, first of all, what are we going to use in this analysis? The stereoplots and cyclographs. What are they? They are stereographic projections, and in order to have, just to understand what they are, consider that here it's the main, for example, the equatorial ring of the body, and this is the plane that we are using in order to identify a groove. So in order to consider only the orientation of planes with respect to a common reference plane and not their spatial distribution, all planes should share the same center of reference sphere. So typically, when we have a plane, that is this one right here, and we have an eye here, what is the representation of this plane here is this is the projection. This is called cyclograph projection, while the pole and the set of pi first represents the stereoplot. In addition to that, the point pi can be represented using also two angles, which is the deep angle A of pi, which is this value here, and then delta, which is the deep direction of pi. The problem is that on small bodies, we have to consider two types of reference system. We have to consider the absolute reference system, which is the one with respect to equatorial ring of Phobos, for example, and then a relative one. So in this work, we are shifting between one reference system and the other in order to understand what are the radial grooves coming from an impact crater and what are the parallel grooves resulting from the same impact crater. So the boundaries that we were using, the criteria, is to use, for the case right here, for example, plane number 1 and plane number 2 fitting a set of grooves. Regarding a relative reference system, we are just using all the poles that are pointing towards 20 degrees far from the north of the cyclograph that we are considering. And regarding the absolute reference system here, we are just considering the radial guys, so they have nothing to do with the north and south reference system, just pointing towards west and east, and we are using the boundaries between plus and 20 degrees. So we identified 352 grooves on the surface of Phobos. You can see that they are almost everywhere, also crossing Stickney, while there is a region that we call occultus region, which is not showing anything right in the middle here, but there are a lot of grooves coming from this region right here. So then we decided to consider the Stickney crater, and we observed that, considering the boundaries that I was showing you before, we got around 5% of the total amount of grooves that depends on the impacting the Stickney crater emplacement, while there is just around 1% of parallel grooves. Here you see in red there are all grooves that are radial, while in green there are the parallel grooves. Then we consider Gulliver crater, which is another one, which is pretty big here on the surface of Phobos, and 3% of the grooves that we identified are related to this Gulliver crater, while around 10%, 9.4%, are parallel. On Flimnap, another crater right here, we got 1.7 radial and 7.7 parallel. And then there is this region. Even if it's not a crater, we were considering it like a possible pass cratering surface of the body, but it's pretty difficult. You can really see here through the shape model. Nonetheless, 6.5% of the total amount of grooves seems to be radial to this region right here. So here you see the entire results of the grooves on Phobos, depending on the emplacement of the 3 craters here and this occultus region right here. And our results show that there are just grooves related to main craters on the body of Phobos, which is around 30%. Of those, 10% are radial. So keeping in mind that there are other formation scenarios, such as the grooves being chains of secondary impacts, they cannot just explain the total amount of grooves that we have detected on the surface of Phobos. So we should consider a different origin for most of the grooves of this body. So right now, one idea that Bukowski et al. In 2008 presented is that on Eros, there are lineaments that are not related to specific craters on the surface of Phobos. So the idea is that they were suggesting is that there was an impact of a former parent body, an impact on the former parent body permitted to the formation of grooves on this parent on this body, and then after several impacts, these grooves were the inherited signature of this parent body, and the resulting Eros was showing these scars. So we think that Phobos has the possibility to be to present the same trend of Eros, and even if our analysis does not hint in favor for an asteroidal or an in situ origin of Phobos, we have to think that it's a bit difficult to have an object like a rubble pile in orbit close to Mars, well inside the Roche limit, and not being disrupted. In addition, you see that grooves are pretty geometrical on the entire body, and if you have really a lot of difference inside it, when you got an impact, it's difficult because there are waves, and it's difficult if you not have an homogeneous body to have such a geometrical presence of grooves all around Phobos. So it's a bit difficult to consider Phobos like a rubble pile. In addition to this, we think that Phobos is pretty cohesive, and it's difficult to be not because after an impact like the Stickney one, which is a 9 kilometers impact crater on Phobos, it was not affected by any disruption. So it has to be a considerable internal strength. These results were presented and accepted after a review by Duxbury, and it was presented and accepted in Icarus, and this is the paper that you can go online and have a look at it. So thank you.
So in Stan Peel's review chapter, he estimates the internal strength you would need in a Phobos to have it still be intact where it is. It's very low. So you need very little strength for Phobos still to be intact, even though it's in its formal Roche limit.
Yeah.
I remember, I think this was by Eric Asfog and Jay Malash, that their early models of Stickney seem to suggest that internal dissipation was actually helpful in helping to avoid disrupting Phobos by the Stickney impact.
Yeah, that's right. I remember I've read that paper, and they were also considering the presence of ice inside Phobos, which is a bit difficult because from the spectra that we are getting, there are no signatures of ice. Still, I think that a mission would worth to go to Phobos and Deimos, because at the end they are both satellites, and they are the remnants of something of the inner solar system, and we still don't know their origin. So it's something that is really required in order to understand where they are from and how they evolved. Let's thank our speaker again.